organizations, and then we'll make the SI announcements. You want to post it? What did you do?
All right, whose speakers are too loud? Thank you.
And yeah, I can zoom out. In or out? Like that? Here you go.
Hello, my name is Dora, and I'm with DHW, which stands for Daniel Hale Williams Pre-Medical Society. And we're having a health disparity forum next Tuesday. It's on there, you can read it. It starts at 5:30, but we're serving food, and it's being catered. And it's, how many of you guys here are pre-med or going?
How many are pre-med? Ask how many are not.
How many? Okay. That's a bad question to ask. Okay. So it's really important that you come to hear things that are going on in the health fields nowadays. And we'll really appreciate if you guys came out. It's free food, it's being catered, and it's good.
Free food?
Yes, free food. So we hope to see most of you there. Thank you. And I have flyers if anyone is interested.
Hi. Okay, so I have an announcement, and it's not about chemistry, believe it or not. A week from tomorrow starts formal recruitment for all sororities, and I'm here to encourage you to register for formal recruitment, which means that you go on the internet and say you want to register for formal recruitment, you fill out a form, you show up, and then, you know, sororities happen. So you should probably consider it. If you have any questions, talk to any Greek woman on campus. I'm sure they would be thrilled to answer them for you. Oh, and this is also not related to chemistry, but I found a toy in this classroom. If it is your toy and you can tell me 2 things about it, and I will ask you those 2 things, then you can have it. If not, then I get to keep it.
No, you don't. Okay, and now about the SI schedule. So Srav is going to have a session this Sunday, okay? So Sunday, 2 days from now, she will have a session. It's in Wade from 6 to 7:30, okay? So there is a session on Sunday. There will not, however, be a session on Monday. Tuesday, we're going with 4:30 to 6 in Clap 108. We don't have that room reserved, so we're all just going to show up. Hopefully, there's no one in it. And Wednesday, there might be a seminar.
Chemistry. I don't know.
It'll be chemistry either way in Clap 108.
All right, if it's not in Clap 108, we'll come here to Schmitt. But show up to Clap 108 on Tuesday. And finally, on Wednesday, we're thinking it'll be in here, but we're not positive. So sometime over the weekend, you'll get an email from one of the 3 of us saying where Wednesday's session is. Okay? And then as of the following week, we'll have a set schedule locked in with all the rooms that won't be changing. Okay?
So how many of you are in Bio 214? Oh, good. Mondays and Wednesdays. How many are also in Chem 113? Oh, so you're here from 11:30 until 5 on Mondays? Oh, just bring a sleeping bag. What? 113 meets in here at 4 o'clock on Mondays. 260. Yes. All right. You don't know where there's any crystal lattices, do you?
Any crystal what?
Lattices.
Crystal lattices, like sodium chloride. What do you mean?
Yeah, those models.
Oh.
Laying around the apartment. I'll just have to do it without them.
Do you need me to draw those pictures for you?
Nah.
I could.
You could if you want. I don't want to. Yeah, go ahead. Go ahead. We're going to let Amelia do this today. All right, let's talk about solids a little bit more, and then we'll move on to transitions between phases. First of all, hopefully you've all dropped the problem into the digital Dropbox for me that figured out the radius of a copper atom, right?
Didn't you say it was Monday?
Yeah, you said it was Monday.
I don't think I said Monday, did I? All right, you can have till Monday. Those of you who've already done it, you can have the weekend off.
I just need to get a...
Crystal lattices. When you talk about solids, Amelia's going to do our artwork for me today. Crystalline lattices, there are several different kinds we have to talk about. So far, we've concentrated on what is the ionic lattice, in other words, the arrangement of ions in a crystal a solid crystal. And what holds that lattice together? If you take and think about the fact that sodium chloride, as we have said, is alternating sodium ions and chloride ions in all three dimensions, and it takes on, if I look just at the sodium ions, a simple cubic lattice. If I look just at the chloride ions, it's just a simple cubic lattice, where a simple cube is one where there is an atom or an ion at each corner of the cube, and it repeats in all dimensions. Sodium chloride would be alternating sodium ions and chloride ions, and the attractive force between the ions is what holds it together. If you think about the chemistry now of a solid compound, remember what we said last semester. I don't care what the nucleus is. We are not going to do nuclear chemistry in this class until late April. And so what matters is, where are the electrons? We want to find the electrons in these lattices. So in a sodium chloride or a simple cube, if I've got the nuclei centered on the corners of the cube, where are the electrons? Well, remember back in physics when you talked about charge density and you drew these maps and it showed that the charge density was focused at the edges and at the points of sharp structures? And it would radiate out from that. The reason for that is because the electrons are going to be localized near those points, near where those atoms or ions are located. And so the charge density in a simple cube is related to that. If I want to do chemistry on a solid material, say I've got this block of aluminum about yay big, 1 cubic foot. Does the chemistry that is happening to that block of aluminum happen with the outermost atoms or those in the middle?
Outermost first.
Outermost. The rest of them are protected. The electrons are inside this structure. So if I want to do chemistry on a solid material, I'm only going to be doing it on the edges. And so yesterday we had a seminar speaker who was talking about the way that she was improving catalysts. A catalyst is a compound that's going to speed up a chemical reaction but not get consumed in the chemical reaction. And many catalysts are heterogeneous catalysts, which means that you may have a liquid phase running over a solid phase, so you have different phases in interaction with each other. Solid materials make great catalysts because the compounds can interact with those surface atoms and then move on through it. The catalytic converter in your car is a bunch of round beads of platinum and palladium. And the gas flows over these things. Well, why are they round beads, first of all? If you want to maximize the surface area of something, you make it a round sphere. And so those beads are coated with this metal, and you've increased the surface area so you have more reaction surfaces going on. That's going to be true in most solid state reactions. If you increase the surface area, you increase the number of faces or edges of the atom, you're going to get more going on. The simplest example you can think about that you may have seen is those of you who have spent any time in a rural area know that grain silos are very hazardous. Grain silos are hazardous because if I take a 2x4 and I light it on fire, it will burn. If I take that same 2x4 and chop it into nice little pieces, it will burn a little faster. If I take that same 2x4 and run it through a grinder and grind it up into a pulp, so I have lots of fine particulate, it burns instantaneously because of the surface area. Chemical reactions are going to do the same thing. What's the matter?
How do you want me to draw that one? Just the triangle or the whole thing?
That's good. I like it like that.
Just without anything?
I think that's worse. Never mind. No, that's good. I like it. Just leave it just like that.
No atoms?
No, you've got a face-centered cube. You've got a simple cube. The body-centered cube. Yeah, it's hard to put the atom into it. It gets ugly. Go ahead and put one in the upper right, lower, back right, front left.
This one.
There you go. Oh, see, it gets hard to do it. Yeah. They look like they've got bigger as you go along. It's a perspective thing. I was never good at perspective in art either, so. There we go. All right. There's nice pictures in my office on the whiteboard if you come up and look. Amelia drew them for me Wednesday. That works. Oh, you only want half. There you go. If we think back now to there's different kinds of solids that we want to talk about. Ionic solids, covalent solids, and metallic solids. All three of these are going to take one of these, in general, one of these simple cubic arrangements. Nature likes symmetry, so they try to arrange things as symmetrically as possible. And each of these three structures, the simple cubic cell, the body-centered cubic cell, and the face-centered cubic cell, have their advantages. They take up different amounts of space. The total amount of space that's filled by them is slightly different. If you've got a +1 and a +1 and a -1 ion, you'll take one arrangement, where if you have a +1 and a -2, you'll take a different structural arrangement. But most crystalline solids are going to be like this. If I take sodium chloride, which would be an example of an ionic solid, if you've ever looked at a micrograph, a picture of it under a microscope, you know that it's got very sharp edges to it. When you break a crystal of sodium chloride, it cleaves, it breaks between the sodium and chloride ions, and you get sharp faces on these things. And if you want to take that crystal, you can just go in with a chisel, hit it on there, and hit it sharply, and it breaks into nice chunks. You can actually do it with your hands with sodium chloride. Because what's happening in that regard is you've got the sodium ion, which is giving up its electron, and the chloride ion that's taking it, and so it's a relatively weak attractive force between them. You just have to overcome that attraction. If I go to a covalent solid like diamond, you break it the same way, except in diamond now, every carbon atom is covalently bonded to 4 other carbon atoms in a perfect diamond. And as long as as long as every carbon atom is always bonded to 4 others, it's an extremely strong compound. The way that you cut a diamond is you look for places where one of the carbon atoms is not present. So you look for occlusions, you look for holes, you look for places when you're looking through the magnifier where it's not perfectly clear. When you look at a diamond under a magnifier, when you see dark spots, what's happened is one of the carbons won't be in the lattice, in the structure. So there's a hole in there. And so it's very weak there. So if you're a diamond cutter, you take this raw diamond, you look for those spots, and all you have to do is tap it right there, and it's already weakened. It will fall apart. And you get nice sharp facets, nice sharp faces or edges again, because what you've done is you've taken advantage of the fact that the chemical bonds that are no longer there are holding it together. So when you look under the scope of the diamond, and they talk about cut, clarity, carat, and color. Thank you, Dave. Amelia, did you show yours off yet? Oh, Amelia's got one to show off if anybody wants to see it. Congratulations, by the way. There, I've embarrassed her sufficiently. It's the first Friday of the semester. So the cut is just the shape that they cut it in, and they control the shape simply by picking which edges they want to expose. The clarity tells you how many imperfections there are in it. The carat is the weight, and the color is what impurities are in it. Some people like it, a yellow diamond. They like to have those impurities in there. Other people just want as white a diamond as they can get. There are no impurities. If you compare diamond how can I do this? Graphite. Oops, I already have 3. I like the picture in the book better. I'll leave it. Graphite is just like diamond. It's got the chemical formula C. It's just carbon atoms. The difference is that graphite is sp2 hybridized, where diamond was sp3 hybridized. So if you think about an sp2 hybridization, what is the geometry of an sp2 hybridization? Trigoplanar. Thank you very much. Trigoplanar. It's always good to have a straight man in the audience. So every carbon is bonded to 3 other carbons. If it's used sp2 hybrids, what does each carbon atom still have that it's not bonded with? A leftover, not lone pair, p orbital. And in that p orbital there is one electron. So if I take this, and if you think about a trigonal planar, it's a flat sheet of carbon, sp2 hybridized, so every carbon bonded to 3 other carbon atoms. Excuse me. Yeah, that's right. And then a leftover p orbital, and these p orbitals are pointing up all the way along this thing. And then there's another sheet of carbon above it with the p orbitals pointing down. There's an attractive force between these 2 sheets of carbon atoms, but because the p orbitals aren't strongly bonded between those 2 layers, graphite slides back and forth. Graphite is a lubricant, unlike diamond. Diamond is one of the hardest things. Graphite is very soft. Graphite pencils, every time you were writing with a graphite pencil, you're laying down a layer of carbon that is that p orbital overlap. It's a very weak attractive force. The other thing about graphite is it conducts a current, and diamond doesn't. Why would diamond be an insulator, but graphite be a conductor? Because they have that p orbital, and so the electrons move freely. What's a current? Current is flow of electrons. It ends up that graphite is actually only a conductor in one axis. If I were to take those sheets of carbon, I can use them as insulators going perpendicular to that sheet of carbon because the electrons are freely running collinear or planar with those sheets. And so you can check graphite's conductance, and in one axis it will conduct a current, and the other it will not because of the free electrons. Graphite on the other, or diamond on the other hand, completely insulates. The big discovery in the late 80s was Buckminster fullerene. Buckminster fullerene is another form of carbon, they're called allotropes, that no one had seen. C60 is its generic formula, and C60 is in the shape of a soccer ball. If you look at a soccer ball, you will find out that every seam how do I do this? I'm very bad at this. There we go. 1, 2, 3, 4, 5. There we go. This one becomes 6. Anybody got a soccer ball with them? One, two. That's close, isn't it? If you keep going, if you look at a soccer ball and you can find out that there is a hexagon at the top, the next row of shapes will be a pentagon. The row after that are hexagons again, and it's an alternating hexagon-pentagon shape. Every seam, though, has 3 things attached to it. They all come to a point with an sp2 hybridization. Because of the alternating hexagons and pentagons, what happens is it naturally curls in on itself. And when there are exactly 60 of these, it makes a sphere. If you take your soccer ball and just label each joint, everywhere the seams come together, you will find out there are exactly 60 points on this thing. Now the story goes that Richard Smalley, who was one of the Nobel laureates who got this, figured out this structure playing soccer with his son in the backyard. They'd seen this structure, they knew it was very regular, they couldn't figure it out, and he was in the backyard playing, and all of a sudden it hit him, and so he goes in the house and starts folding origami, pieces of tissue paper, into this shape, and got on the phone immediately to Curl, his collaborator, Robert Curl, and said, "I've got it," and then went in and put this thing together. The thing they found out about this, though, is once it curls on itself, you can actually get other forms too. So there's C72. 72 carbon atoms will also make a distorted soccer ball. What it does is it repeats one row of hexagons in the middle, and so it's kind of like a rugby ball. And as you keep adding to these, every 12 you can get more stable configurations. Could you have less than C60? It ends up that once you start getting less, you go to C48, theoretically it would be stable again. But if you try to fold pieces of paper to make the shape into C48, you find out that it's too tightly bound. Because what do you know the bond angle of this to be if it's sp2 hybridized?
Less than 120.
120, not less. It's a perfect. But because it's bent in. Why is it bent in? It's bent in because as you keep going, it naturally pulls in. So it is going to be a little less than 120. Okay. I'll agree with you then. If you go to C48, it's really less, and so it's too strained. It breaks apart. The other thing, though, is if it's sp2 hybridized, what does that tell you? There's an unused p orbital. So imagine that soccer ball with a bunch of spikes sticking out of it, which are p orbitals. Now imagine you had 2 of these, or a whole array of them. What's going to happen to those p orbitals on those soccer balls? They're going to interact and stick together for a little while, but they're also going to transfer electrons. So you end up getting conductivity of these things rolling back and forth. C60 is a superconductor. It conducts phenomenally well because of that unbonded p orbital. The other thing, though, is if there's spikes sticking out, this is a p orbital, there's spikes sticking in. So if there's spikes sticking in and there's electrons in there, what do you think you could do with it? You could trap a positive ion in the middle of a C60. And so that's what they've done. They've gone and taken potassium or sodium and trapped it in there. Now, why did they do that? I'll get your question in a second, Mustafa. They put that in there, first of all, to show it could be done, but now it becomes a drug delivery tool. Because if I can put a cationic salt in there, and I can encapsulate it in this sphere, I can inject it into the human body, and it's going to, because of the conductivity, roll along very nicely. Then they can control when it will open up to release that compound. And so they had to come up with a whole new nomenclature for these things. And so they started to say, we're going to put a cation, or we're going to put a cationic salt into the C60. And so we already talked about hydrates a little bit, copper sulfate dot 8 H2Os. Now there is compounds that have this at symbol, which means it's inside of the C60s. And there's a lot of research, because the other thing they've done with it is they said, all right, if I can make spheres, why can't I make tubes? And the tubes are nanotubes. And nanotubes are the things that they're talking about as being useful for superconductivity, because now the same thing. We've got this cylinder of carbon with the p orbitals outside and inside, so it becomes a superconducting channel. And you can conduct current down the whole thing. Mustafa, you had a question?
Yeah, so this would be a solid, but if you like rubbed it on something, would it?
Well, it's a good question. If you were to take this, like graphite, if you were to take graphite and draw it on a piece of paper, what happens? You leave a layer of graphite on the piece of paper, and you can keep doing that. You're just peeling off layers. If you have these spheres of Buckminster fullerene, what if you rubbed it on something? Do you know where they found Buckminster fullerene? The ash from a fire. The soot that comes from burning wood, they have gone back and looked at it, that's a source of C60. So yeah, if you rub it on something, you leave a smear of C60, this black ash, essentially, all over. One of the things that we're looking to do this summer is to put in a synthesis of Buckminster fullerene into the Chem 113 lab, because it's relatively easy to make. And so we're going to try and do some of that. There's a nice little reaction going on right here where there's crystals forming on here as it sits here. I have dry ice in here, by the way. And so there's enough humidity in this room right now that I'm getting crystals forming on here. Crystals are great because once you get one started, they will keep growing and growing. And you've seen it. Icicles are just water crystals that have gotten very large. These, if you've ever seen these frost up like this, you see they're like little hairs sticking out, because once the crystals start growing, they keep growing in a certain dimension. And they're all the same on this. And so growing crystals, I mean, I don't know, call me, yeah, never mind. Where's my, there they are, it's right here. There was one other one here that I erased. Metallic solids. Metallic solids are slightly different from these others, because if you think about sodium chloride, If you rub sodium chloride, it breaks into pieces. You can grind sodium chloride into a powder. But if I take aluminum and I start to grind it, what happens?
It's malleable.
It's malleable. It starts to bend. Copper is malleable. You can get it to bend. Metallic solids, pure metallic compounds, have slightly different bonding, and it's never very satisfying. But essentially what it's described as is a sea of electrons. Again, the metals are going to take on these structures, these simple cubic lattices, but the electrons are free to go anywhere. So there's just this huge sea of electrons. And as you pound on metal, like aluminum or copper, what's going to happen is you start to deform those crystals. And the electrons move out of the way because the attractive forces are relatively weak, so you can get these things to take just about any shape you want. But the other thing you can do, and the next time you, let's see, on your 21st birthday, you can go look on the shelf and you can find this clear liquid that has these flakes of gold in it. I don't know what I've seen it once or twice. It is real gold. You can buy cake that has thin sheets of gold, and what they do is they literally take gold metal and hammer it until it's just thin foil. The gold filigree or the gold on the ornamentation is just hammered gold, and it is what they've done is they've taken the gold and taken advantage of the fact that these attractive forces are so weak, they can shape it into very thin sheets. It is pure gold. Yes, you can eat it. Yes, it will come out in the same form. You don't digest it. So that's why it's the small stuff. Now, if you see the little worm in the bottom, don't eat that. I don't know what has that in it. All right, let me change gears here. The guest speaker yesterday was very interesting. She's a professor at Purdue, and she teaches a general chemistry class. And she said her goal every day in class is, she said, she has a class of 400, and she said she walks in the first day and she says, I'm going to try and make you laugh every 10 minutes. I looked at her and said she's crazy, but then I thought about it and said, everyone, if you can do that, so I never mind. I'll bring the turkey seat out another day, right? I've already done that, got to do something else this semester. All right. If we try to combine all three of these now into the transitions from solid to liquid to gas, every compound can be converted from a solid to a liquid to a gas. I'm sorry?
Carbon dioxide.
What about carbon dioxide? Can carbon dioxide, funny you should mention that, I happen to have a little carbon dioxide right here. Dry ice, right? Why is it called dry ice? Is it that good? Why is it called dry ice?
Sublimates.
No, it doesn't. Goes from solid to gas? Yeah. There's a word for that, and it's not sublimate. That means something else. Go look it up on Wikipedia. It sublimes. It sublimes. The process of going directly from a solid to a gas is called sublimation, but the verb is to sublime. To sublimate is something else. And you can go talk to your health teacher about what it means, what it really means. And if you don't believe me, go look it up. How do I want to do this? Let's see. I guess I'm going to put it up there and we'll talk about it. I want to draw you a representation of a plot of pressure versus temperature of a pure compound, in this case, carbon dioxide. Just take a little bit of carbon dioxide, and we're going to look at carbon dioxide, and we're going to say, okay, if I've got carbon dioxide at a very high pressure and a very low temperature, What phase will it be? Solid, liquid, or gas? Solid. It's at high pressure. You push the atoms as close together as you can. It's at a low temperature. The atoms aren't moving very fast. So at high pressures and high temperatures, high pressures and low temperatures, I'm going to have solid. Do you think that will be true for any compound? Yes. For any pure compound, at high pressures and low temperatures, you have to have solids. What is high? It depends upon the compound. What is low? It depends upon the compound. The scale's going to change in each one. What if I'm at a high temperature and a low pressure? Gas. If the pressure is low, so you're not pushing the molecules or the atoms together, and the temperature is high, so they're moving very quickly, that's the definition of a gas. So for any pressure temperature diagram like this, I can label those two parts of it without knowing anything else about it. In the case of carbon dioxide, I know that there is a transition where solid CO2 transforms to gaseous CO2 without becoming liquid if I'm at room temperature and pressure. There's a transition between them. Is it against the law to handle dry ice?
But he's a BA, so it's all right.
I'm a what? I'm a what? I'm a BA, meaning, how'd you know I had a BA degree? Didn't I tell you that? I think you mean bad something, but that's another story. No, if I hold this, will it burn me? I mean, what's happening as I'm holding it? It's subliming, and it takes energy to sublime. Where is it getting the energy from? Me. And so as it's taking energy out of my body, what's happening to my hand? It's getting burned. Yes, if you handle dry ice improperly, you can get burned, and you saw me get burned last year, right? Yeah, last year I got burned pretty badly from the dry ice. I got a nice little blister and scar from it because I was not doing it well. This time, you'll notice I keep moving it around. I got in trouble at home a couple weeks ago, or months. Do you remember the recruiting day over in Veal when I brought the dry ice in the water with me? One of the senior chemistry students said, "Can I eat some of it?" And you really, it's not a good idea to put this in your mouth. It is kind of nice because all the vapor starts to show up. But you have to keep moving it around because if you don't move it around, it will burn your tongue. Well, if you'll remember, that was the day I brought my 10-year-old daughter with me. She's 10. She'll try anything. "Dad, can I eat some dry ice?" So guess who I got in trouble with? Yes, Mom was not happy that I taught my daughter how to eat dry ice. You do have to keep moving it around. Anyway, there's a transition where if I hold the temperature constant, not the temperature, if I hold the pressure constant, atmospheric pressure, where dry ice will convert from solid to gas without going through a liquid phase. And at some point in between there, both the solid and the gas are in existence. In the case of dry ice, it's hard to hold it at that position. This process of going from solid to gas, as we've already said, is subliming. Okay. If this were water at room temperature and pressure, I know that solid water converts to liquid water without too much effort. And so there must be somewhere in between the solid and the gas, liquid. If I ever ask you to draw one of these diagrams, you should automatically know where the solid is, where the gas is, where the liquid is. It has to be this way. If you're at high pressure, you're pushing the atoms or molecules together. If it's at low temperature, they're not moving very fast. That's the definition of a solid. If you're at high temperature, things are moving fast. And low pressure, they're all over the place. That has to be a gas. And anything somewhere in between, there's liquid. The challenge is to figure out where. Well, there's a line that separates the solid from the liquid. You also know that if you keep heating water, liquid, you can form a gas. And so there's a line that separates the liquid from the gas. This will be true for absolutely every compound we know. There is some separation between the solid, the liquid, and the gas. And it ends up that these three lines intersect. At a single point. Okay? Let's take this thing apart a little bit more. We already know that the process of going from solid to liquid is melting. What's the process of liquid to solid? Freezing. Okay? Subliming, we said, was solid to gas. And so the process of going from gas to solid is happening on this right now. We're taking water from the air and crystallizing it onto this glass because the glass is so cold. What's the process of going from gas to solid? Deposition. You're depositing a solid onto this. You all know that you can also go from a liquid to a gas or vice versa. So liquid to gas would be boiling. And gas to liquid, condensing. Okay? Let me blow that diagram up a little bit. Okay? The hardest part people have with this diagram is remembering which axis is pressure and which is temperature. By convention, pressure is the vertical axis, but it doesn't have to be. It ends up there's a third axis in here too that we never really talk about, which is composition, but we'll get to that one in a little bit. This line right here is the easiest one to understand. That's the transition from liquid to gas. And what this line tells me is that if I'm at some fixed pressure, there's going to be a temperature at which the liquid and the gas, if I were exactly at that pressure and temperature, I'd have both of them. If I change the pressure, I would change the temperature, and vice versa. That line is an equilibrium line. What it says is that if you're anywhere on that line, you have the solid or the gas in equilibrium with the liquid. And so you could convert back and forth between them with no input of energy. When water is boiling, you're converting it from a liquid to a gas. The temperature stays constant. And the temperature won't go up until after you've converted all the liquid to a gas. Once all the liquid has been converted to gas, the temperature skyrockets. But as long as I'm sitting on that equilibrium, it will not change. What temperature does water boil at?
100 degrees C.
100 degrees C. Is that all you have to tell me to say what temperature does water boil at? Anybody from Denver? Shrav's from Denver. Shrav, what water does temperature boil at in Denver? Look on any recipe box, any cake, and there's always high altitude directions. What do you have to do to bake a cake in Denver? Cook it longer. Why? Because the pressure is less, the atmospheric pressure is less. And so if the atmospheric pressure is less, you're on this curve, you're down here somewhere lower. What happens if I lower the pressure to that liquid vapor equilibrium? It goes down. When you're baking a cake, what you're really doing is driving off the liquid. Think about a cake batter. It's very wet. When you bake it, you get rid of all the liquid. So you're boiling off the water when you bake it. You have to have high altitude directions because the temperature of that boiling is much lower. You have to work harder to get the chemical reactions to occur as well. So this is only true at 1 atmosphere of pressure at sea level. When you have 1 atmosphere of pressure, the boiling point of water is equal to 1 atmosphere. Does water evaporate if you're not at 100 degrees C? Yeah, it does. And we talked about why at one point some of the molecules have high enough energy to overcome the attractive forces that hold them together, and so they evaporate off. Once they leave, you have to have more molecules distribute. So this is called the normal boiling point. The normal boiling point is when the vapor pressure equals atmospheric pressure. Vapor pressure being the pressure of the gas of whatever it is you're talking about. When atmospheric pressure equals vapor pressure, the compound is boiling. You can make any compound boil at a relatively low temperature by lowering the pressure. And as soon as the vapor pressure equals that, so I could boil water by putting it in a vacuum. Okay. What's this other point here, which is the junction between the solid and the liquid line? It's the freezing point. What's the freezing point of water? 0 degrees C. So the normal freezing point of water is 0 degrees C. It's the temperature and pressure at which solid and liquid are in equilibrium. What temperature does water melt at? Well, let's look at our diagram. If we freeze, we go from solid to from liquid to solid this way. If we boil or if we melt, we go from solid to liquid. What temperature is this intersection at for those two? Exactly the same point. Water freezes and melts at exactly the same temperature, but I guarantee that if you go home and ask your family, they'll tell you that water melts at a higher temperature than it freezes. Why people think that, I've yet to figure out. They melt and freeze at exactly the same temperature. And once it starts melting, it stays at that temperature until it's all melted. You can't move. The third axis on this is composition. If you change the composition, you change where these lines are. So these all assume a constant composition. So that point is where liquid and solid are in equilibrium. That point is where liquid and gas are in equilibrium. What about that point where the three lines come together? What's in equilibrium at that point? Everything. Solid, liquid, and gas are all in equilibrium at that one point. And since we are real creative people, us chemists, we call it a triple point. There are three phases in equilibrium at the same point in this space. It is a characteristic of compounds. If you know it's triple point, it is a single point. It will always be that. In the case of water, the triple point of water is at about 0.04 degrees C and 1.05 atmospheres. It's almost exactly at its freezing point. There's another point on this curve we have to worry about. This point is called the critical point. That line comes to an end. And if you put yourself into this graph for a second and say, okay, what's happening as I move through the graph? If I were to start at some high pressure and move at a constant temperature and be lowering the pressure, eventually that liquid will become gas. If I were to start at some low temperature and move at a constant pressure, I could convert the solid to a liquid to a gas. There is this area over here, though, where there is no transition. There is a region in this curve where there is no clear demarcation between a solid and a liquid and a gas. And if you're at a pressure or a temperature above the critical point, you can't tell the difference between solids or liquids and gases. The dry cleaning industry is using this to their advantage right now. It's called supercritical fluids. A supercritical fluid is a liquid, or it's a compound that has liquid-like properties, but it's at a pressure and temperature greater than this critical point. And the supercritical fluid that the dry cleaning industry uses is this stuff. Why? They used to use methylene chloride, CH2Cl2, to dry clean clothes. And all that dry cleaning means is there's no water. It doesn't mean there's no liquid, it means there's no water. Methylene chloride, if you draw the dot picture for CH2Cl2, you find out it's a polar molecule with a relatively low molecular mass, so its intermolecular forces of attraction are dispersion, dipole, and that's it. It boils at a relatively low temperature, so you can wash clothes in methylene chloride. Because it's polar, it attracts the same kind of dirt and junk that is in that other cleaning solutions use, but it evaporates very quickly because its boiling point is so low. But they're putting all these chlorofluorocarbons into the atmosphere in the dry cleaning industry, so they were the bad guys about 20 years ago. So they said, let's find something else. So you take supercritical CO2, and it has water-like properties, liquid-like properties. And they can use it to dry clean things, but because it's a gas, you can pull it off very easily. And so now they're dry cleaning clothes with CO2. So the CO2 in the atmosphere, that's okay. We use it to clean clothes now. Guess who else uses it? The restaurant industry. Because it's a great way to kill bacteria. They can't exist at these pressures and temperatures. And so you put food through there, and the bacteria are dead, but you have the food preserved. And so the food industry is using it too. You're going to hear a lot about supercritical fluid CO2 in the not too distant future. It's already being used quite a bit. Last thing about this. These other two lines, the solid equilibrium lines, that one and that one go on as far as they have to. They don't have a terminal endpoint.
So is the line between the solid and the liquid, is it always going to be so that if you maximize pressure, it'll become a liquid versus a solid?
It's always nice to have someone in the audience to ask the correct question. There are only two ways to draw this diagram. One has that line sloping to the left. The other has that line sloping to the right. The solid liquid, or the solid gas line is a curve that you need to have quite a bit of information to know about. The liquid gas line is this curved line that you need to know something about. Both of them slope from left to right. The solid liquid line changes from a slope from right to left in the case of water to left to right in the case of most other things. CO2, for example, would have a slope from left to right. This one is water. And the reason why the slope is different is what's the difference between, and I'm going to do this over the weekend so I can prove it to you. solid water compared to liquid water as compared to a solid organic compound and the liquid of that same organic compound. Ice cubes float. Solid organic compounds sink. The density of the solid, if it slopes from left to right, is greater than the density of the liquid. If the density of the solid is less than the density of the liquid, it slopes from right to left. And so you can identify that with that. Are the divisions always linear? How do you mean? Yeah, okay, I know what you're getting. Yes, they're not always straight lines. They're usually curved lines, okay? One last thing before you take off for the weekend. I'll email you some suggested problems to look at from the chapter until Kappa gets up and running. But here's your challenge for the weekend. Rumor has it that ice skating works because of that phase diagram. Explain to me, you think about why would someone say that you can ice skate because of that diagram? I know. And I'll tell you that the answer is not right. And we'll talk about it first thing Wednesday. You can send me your guesses if you want. I gave you your phone back, didn't I?
Yes, you did.
All right.